Hi guys, and welcome to this video on similar solids. It's basically following on from a video I recorded about 3 minutes ago on similar figures. So if you haven't watched that video, go back and watch it. It's not very long. Hopefully it will make sense and it will lead very much into this. My name is Darren from Maths Guru. Thank you very much for watching. You're going to say, what's Maths Guru? It's my little corner of the interweb where you can go, sign up for free, watch these videos, download lesson notes. VCAR questions, the world is your oyster. But before I get started, this is the needy bit. Stop watching now, mother. Can you subscribe to my YouTube channel, please? Very few people out there watch maths videos. Surprisingly, not. And those of you who do and are watching this video, if you can go to Maths Guru YouTube channel and just hit subscribe. Turn off notifications if you want. I promise you I don't spam you. But if you can go over there and subscribe, it genuinely means the world to me. I am really quite sad and lonely. I sit in this room talking to myself, and just knowing that someone out there click subscribe is greatly, greatly valued. Now, I would normally go through the stuff here, but God, you can read that. It's basically just saying we're going to look at, solids and scale factor. And whenever I use the word solid, I feel a little bit unclean. But again, we'll leave that conversation there because this is for schools. Now, I said I've already built on a video from previous, where basically we turned around and we said, well, if we had two rectangles, where, for example, this side length here is 3, and that is 2, and we make that 6 and that 4, we can see quite clearly that we've obviously doubled our side lengths. We've taken every single side length and times them by 2, and therefore they become a similar figure. So long as I multiply out every single side by the same constant, that is awesome. Now again, in maths language, a constant here is called the ratio of side lengths. So we can find this ratio of side lengths quite easily by taking two sides and dividing them. We then went on to say, well, hold on a moment, what about our areas? And we noticed that our ratio of areas was basically our ratio of side lengths squared, as in times by itself. And normally I don't explain it this way, but what I wanted you guys to understand was that if I am taking this side and doubling it to get to that side, let's write that down. And I'm taking this side here and doubling it to get to that side, then what I'm doing is I'm doubling the shape that way, and I'm doubling the shape that way, which would mean that my area is actually going to times by 4. And that's very much why we take the ratio of side lengths and square it. Because if I am making this 2 times bigger, making that 2 times bigger, my area has to get 4 times bigger because I'm effectively fitting 4 of those shapes in than what I had before. So let's move on to a similar solid. Again, I hate the word solid. It makes it sound like poop, but that's a whole new discussion. Now, a solid is basically a 3D shape. So here we have a wonderful example of a cuboid. All right, so there is a 3D shape. We got cuboid A and we got cuboid B. Now, I've deliberately looked at it this way, so I've gone from a bigger shape into a smaller shape. But the rules don't change from similar figures, okay? The ratio of the side lengths. You take the side length of an image and you divide it by the side length of the original. So again, let's label this. Which is which? This one here is my original. He says not being able to spell. And this one here is my image. So if I wanted to find the ratio of those side lengths, I would choose a side length on my image. Let's choose that one there as 3 and divide it by the same side on the bigger one. So image would be 3 divided by 9. And again, I would probably leave that as a fraction. I wouldn't put that into my calculator because it would come out as 0.333333333, and that's not necessarily helpful, right? But it's building on that knowledge before. What about the volumes of similar shapes? Last one we looked at areas because they were similar figures. Now we got a similar volume. Well, my volume, so what happened here? So this side here basically got 1/3 smaller. This side here got 1/3 smaller. And that side there got 1/3 smaller. So could this work in the same way as we did before? Well, I should Coco. So I'm actually going to, because I think this is a bit confusing, I'm actually going to pretend we're going to do it this way. It actually makes life a bit easier if I do it this way, right? And then we'll just backtrack it in a moment. So let's say that that was 1, has gone to 3. So if I was using that cuboid B to cuboid A, I'd say that it's got 3 times bigger in height. What about this? It's gone from 3 to 9. It's got 3 times bigger along that way. And what about going backwards? It's also got 3 times bigger. And much like the last time, what would be 3 times 3 times 3? 3 times 3 is 9. 9 times 3 would be 27. So believe it or not, in this situation, if I was going from this volume to that volume there, we would notice that this one here would be 27 times bigger than that one there. All right, so what we're really doing here is we're taking the scale factor enlargement, or the ratio of side lengths, and we're effectively timesing them all together for the 3 dimensions. And that gave me 27. So going back to our example a moment ago, because we know that the scale factor enlargement here is 1/3, we'd be looking at doing 1/3 times 1/3 times 1/3, which is 1 on 27. And again, I've done that in my head. You can use your calculator as long as you've got it in exact mode. Yeah, so is there a nice way of checking this for other shapes? I should go. Right, let's have a look at the cylinders. Let's find the ratio of the side lengths first. Oh, he can't write in highlighter, so the ratio of the side lengths is equal to, right, so which one is my original? So that's my original, and this one here appears to be my image. So we choose one side on my image, so let's choose that 3, and the other side that matches is 6. So I'm going to do 3 divided by 6, which is 1/2. All right, so the ratio of the side lengths is 1/2. So what does that now mean, the ratio of the volumes? Well, the ratio of my volumes is going to equal, well, how many dimensions does this shape have? Yeah, it's 3-dimensional. It's a solid shape. It's got 3 dimensions. So in which case, I'm going to take my scale and my ratio of the side lengths and then raise it to the power of 3. And again, that just means that's 1/2 times 1/2 times 1/2. Again, I am bringing my shape down 1/2 that way, 1/2 that way, and 1/2 that way. So 1/2 times 1/2 times 1/2 gives me 1/8. So that's my ratio of my volumes. I'm fairly sure that if I use my calculator, maybe I'll leave this to you. If I use my calculator to work out the volume of that shape there and work out the volume of that shape there, I bet that this one here is 1/8 the size of that one. If you're not sure what the volume of a cone is, it is pi r squared times h, where r is the radius and h is my height. All right, I'll leave that to you. Pause the video, go back if this doesn't make sense, and let me know what's happening. What about cones? Does it work for cones? Absa-posa-flippin-tilly-loodly. Let's just actually do it with the calculations then and go back and check the sort of the theory, as it were. God, I've gone very high pitched. So let's do the volume of cone A. So the volume of cone A is given by, what's the volume of a cone? I don't know. Yes, you do. I've written it here. The volume of a cone is given by 1/3 times pi times radius squared. Do I know the radius of my cone there? 1.5. Yep, so 1.5 squared. And I'm going to times that by my height of 5. Can't do that in my head, but I have a calculator, so why would I do it in my head? So I'm going to do 1 divided by 3. I'm going to times that by pi. Again, Texas, why couldn't you have had the pi button separate? Times 1.5 squared times by 5. Hit enter. Ooh, we get a horrible value. So let's just say 11.78, all right, for this moment in time, centimeters cubed. What about the volume of the bigger cone? So let's say volume of cone B is also going to be 1/3 times pi times, let's actually bring it in, radius, it's just 6 squared, times by my height of 20. And bring up my calculator. It's on and off, on and off, on and off, off, off. So let's do 1 divided by 3 times by pi. Sorry, guys. I don't know what's going on with my calculator today. Times that by pi. Times that by 36, because I know what 6 squared is. Times that by 20. Hit enter. Gives me 753.98 centimeters cubed. All right, let's work out what our scale factor of enlargement is. How are we going to do that? Well, remember, if we know the volume of the bigger one, and we know the volume of the smaller one, we actually just divide them. So I'm going to take my calculator and I'm going to say, well, let's do that. Divided by the one I got before. Notice I'm not using the rounded values, I'm using the whole values, and I get 64. What? So therefore, my scale factor enlargement for my volume is given by 64. That means that the volume of this one is 64 times as big as that one. But was there another way we could have worked it out? Oh, of course there is. There's always other ways of working things out in maths. Right, let's work out this ratio of side lengths. Let's call that the ratio of side lengths is given by, well, what do we need to do? We take one side and divide it by its similar side. Okay, we can do that. So we can do 20 divided by 5, which gives me 5, 10, 15, 20, which gives me 4. So I would now know that my ratio of my volumes would be given by 4 to what power? Well, it's a three-dimensional shape. So we've grown it 3 times that way, 3 times that way, and 3 times that way. So that's why we raise it to the floaty 3, which is 4 times 4 times 4, which just happens to be 64. Now, I don't know about you. Given a choice, I'd probably want to do that calculation there than that one there, because this could possibly lead me to errors, particularly when my calculator hates me and won't let me do pi when it needs to. So bring it all together, and this is great for your summary books. Again, summary books are really useful in Australia. If you're not allowed to use them around the rest of the world, sorry, you've got to remember it. But bringing it together from previous video and this one, for two-dimensional shapes, the ratio of the areas is given by the ratio of the side lengths with a floaty 2. Why? Well, because area is two-dimensional, yes? You're growing it that way and that way. That's the only way you can grow areas. It's flat. Areas are flat. For 3D shapes, we notice that that's a floaty 3. Exactly the same formula here. It's just got a different floaty number. Whee! That's really, really awesome. Here's an example. Two solids are similar, such that the larger one has all of its dimensions 3 times that of the smaller one. So they haven't told me what the solid is, so I'm just going to draw some sort of cuboid. There's my original cuboid. What have they told me? That the ratio, so the large one has all of its dimensions 3 times bigger than the smaller one. So it's telling me that that's got 3 times bigger. Well, if that's the case, I know that my ratio of side lengths must equal 3. How many times larger is the solid's volume? Oh, volume. Well, it's 3-dimensional. So therefore, we know the ratio of the volumes is equal to the ratio of my side lengths cubed. My ratio of the side lengths was 3 cubed, which is 3 times 3 times 3, which is 27. So there we go. So I now know the ratio of my volumes. The volume of this one is 27 times bigger than that one. Sheesh. A solid has dimensions 7 times larger than those of a smaller similar solid. All right, let's do that again. So let's try it again. What do we got here? A solid has dimensions 7 times those of a smaller one. Oh, you can't draw anymore. What's going on? So there we go. There's one. And there's another one. So what we're saying is my ratio of side lengths is, a solid has dimensions 7 times. So let's make that 7 times bigger. How many times is the volume of the larger solid greater than the smaller? Well, I now know that my ratio of side lengths is 7. So therefore, my ratio of volumes would be equal to 7. How many dimensions is the shape? 3 dimensions cubed. 7 times 7 times 7, which is way too big a number for me to do in my head. So I'm going to do it off my calculator. 7 times 7 times 7 gives me 343 times bigger. That's massive. And believe it or not, that's pretty much all there is to this section. Yes, they may try and throw in a couple of curveballs. They may actually give you the ratio of the volumes. So if I look here, they actually may have given you the ratio of the volumes and asked you to find out the ratio of the side lengths. Well, let's just write that on here so that you've got it handy for your summary book. Yes, the ratio of the side lengths is equal to the ratio, let's try that one again. as the ratio of the volumes is equal to the ratio of the side length cubed, we would know the ratio of the side length would equal to the cube root of the ratio of the volume. So if they've actually given me the volume, I'd find the cube root. Let's see if I can find that on my calculator. Well, yes, so in this situation, I'd hit Control and this up arrow button there, and you'll notice that I can now put 3 in there and whatever my ratio of volumes is. So again, if I put 343 in, I would get 7 out, which was my ratio of my side length. So again, that's a little thing in there just in case they try and throw you a curveball. But I'm going to call it a day for this video. Thank you very much for watching. Hopefully it's been useful. More videos coming in the series and lots more videos across mathsguru.com. Please subscribe if you can. Again, it means the world to me if you actually do. And I've got absolutely no friends and no life. So, yep, we'll leave that one there. Hopefully I'll see you in another video. Take care and stay safe.